These first three multiple choice questions are based on the same reaction. Carbon dioxide can be prepared from adding dilute hydrochloric acid to calcium carbonate powder in a test tube. So let's draw a little picture of that. Here's my test tube. I'm going to put some calcium carbonate powder down at the bottom, and in it I'm going to add, in this story, 10 centimeters cubed of hydrochloric acid. It then says to me, if 15 centimeters cubed was added instead of 10 centimeters cubed, how is the rate affected? Let's look at how this reaction takes place. Remember, a reaction takes place by collisions. So there'll be collisions only happening in this part over here, where there are some hydrochloric acid particles coming into contact with some calcium carbonate particles. There's no reaction happening up at the top there, where there are no calcium carbonate particles. So now, if I put a little bit more of this HCl in here, I find that absolutely nothing changes. At the reaction site, I still have the identical surface area of calcium carbonate. I still have the identical concentration of hydrochloric acid, and I still have all the same conditions at the bottom. So that is going to make absolutely no difference to my reaction. But if I add more calcium carbonate powder, I have just created more surface area on which collisions can take place. And therefore, I have just increased my rate of reaction, because there are now more collisions taking place because there is more solid surface area. So adding more powder has added more solid surface area to the situation. If I take the temperature and I decrease it, all the particles will move more slowly inside there, which means that they will bash into each other very slowly. As a result, the rate of the reaction is going to decrease. Why does a chemical reaction proceed faster if it is stirred? I am forcing more particles to come into contact with each other. The reactant particles are forced to collide more often. Remember what makes chemical reactions go fast? More collisions, faster rate of reaction. An excess of zinc powder is added to copper sulfate at 20 degrees centigrade. Let's think about that reaction for a second. We're going to say zinc plus copper sulfate is going to form copper plus zinc sulfate. Notice, zinc is a metal, it's a solid. Copper is a metal, it's a solid. Zinc sulfate is a solution, aqueous. And zinc sulfate will also be a solution, aqueous. So I've got no gases, so pressure is not going to make any difference to what is happening here. Temperature always makes a difference. If the temperature rises, as they tell me, to 30 degrees, that means this is an exothermic reaction. It means that it is releasing energy. Heat is coming out of this particular reaction. So B, it is exothermic. If we take that same reaction and we say that the copper sulfate solution is blue, and it slowly becomes colorless. Why? Because it is this copper 2 plus ion that actually contributes to the blue color. And I'm losing that Cu2 plus, and it is becoming copper metal. So the color slowly gets lighter and lighter. Which of the following could not be used to measure the rate of the reaction? Conductivity can be measured because it's a change in ions and how well they conduct. It's not great for this one, but it could possibly be used. The reason it's not great is because you've got ions on the left and ions on the right. The temperature change over time doesn't tell me how fast the reaction is going. It just tells me whether it is an exothermic or an endothermic reaction. The color change does make a difference, and the mass of copper, how much copper is being produced, does make a difference. So these two are good ways, the color change is a good way, the mass of copper is a good way, the conductivity is a iffy way, but definitely the temperature is not going to work. So temperature over time is not going to work. Which of the following reactions at constant temperature has the fastest rate? So I'm looking for the highest pressure. If I want the highest pressure, I need to look at these prefixes. 3 of them are in kilopascals, 1 is in megapascals. Now mega means that I need to multiply by 1,000 to get to kilo. Let's just take a look at that. Kilo is times 10 to the power of 3. Mega is times 10 to the power of 6. So the difference between those is 1,000. So I am going to have to multiply by 1,000, and therefore I get 10,000 kilopascals. And that is the highest pressure of the ones represented over here. The mass of catalyst was determined at intervals, which is the change in the mass of catalyst. Remember, a catalyst does not change. It stays constant throughout the reaction. It only lowers the activation energy. So the graph that shows no change in the mass of the catalyst is B. The following equation represents a common way of preparing carbon dioxide in the school laboratory. We've got calcium carbonate and hydrochloric acid giving me calcium chloride, carbon dioxide, and water. Which of the following methods does not increase the rate of CO2 production? If I increase the temperature, I definitely increase rate. If I increase pressure, I increase the rate of a reaction with gases. There are no gases here. So pressure is not going to help this particular reaction go faster in the reactants. Increase the concentration of hydrochloric acid. That sounds like a good idea. It increases the number of particles of hydrochloric acid, so that would mean more collisions. And if I increase the surface area of the calcium carbonate, that would also make it go faster. So the only one that doesn't work is increasing pressure. With reference to the below curve, consider which of the following statements is false. An increase in temperature will increase the average kinetic energy of the particles. This is true. A catalyst will increase the number of particles with sufficient energy to react. Now remember what is going to happen with a catalyst. Catalyst is going to lower the activation energy. So if the activation energy is lower, that will mean more particles will be available to react. A catalyst will decrease the activation energy. The energy of the particles increases during the course of all reactions. This is simply not true. You've got an average energy for the particles in a reaction. It doesn't increase or decrease. All that I can shift is what is the activation energy. I would need to change the temperature to change the energy of the particles. So D is my only answer that is false in this particular case.